Lesson 3 makes a big jump and starts to talk about volumes. And we're going to split this up into about 3 days. The first day is going to talk about how we deal with cross-section problems. And so that basically means we have a base of a certain shape, and from that base kind of popping out at us, we're going to have the same type of shape all the time, whether it's squares or rectangles or right triangles or semicircles. We're going to have the same sort of shape always popping out at us. So we're going to look at 3 examples. We actually start with example 3 randomly. But in this question, we're going to have a parabola of y equals 4x squared. And then we're also going to be looking at x equals 1 and the x-axis. We're going to look at the area that's kind of bounded by that shape. And then popping up from that shape is going to be squares. We want to find the volume of that overall idea. So this is my attempt to be artistic here. You're going to have to really work at understanding some of my pictures because I am not good at drawing this. But basically, in the shape that's on the left, this is the parabola 4x squared. This is the line x equals 1. And what we're going to do is put in just a couple of vertical lines here. Each one of those shapes, there's going to be a square that pops up at us. So if you think about what this would look in 3D, it's going to be really short here, and as these lengths get taller, the overall shape gets taller as well, because what we're basing these squares that are popping up on is the overall width that we have. I'm sorry about that there. What is going on there? Okay, so from there, I decided to make a kind of almost take this picture and lay it flat. And so that's what you're seeing in the second picture. And so the red lines from the first one, now they're going to be laying at more of an angle, and from them, you're going to see, let's see how this works here, you're going to see some sort of a square that is popping up at each one of these. So this one will be a little shorter because the base is not as big. So that's kind of what we're doing. Then we're going to try to add up all of these different mini squares together to get the overall volume. So what I like to do with this is to actually draw a bit of a shape, if that helps you. And my horrible artistic skills are made even worse by drawing on an iPad here. But so we're going to have this sort of shape to represent the volume of one of these little red pieces, adding a little width. Because this is a square, it makes life a little bit easier. The base, this length of red line here, is the same thing that I would see here. So this piece corresponds with that piece. And that overall width is whatever y is there. That's going to be 4x squared. And because it's a square, the height of this will also be 4x squared. And then the width, this piece right here, is going to be something that we have to add to that. That's going to be what we call dx. It's the change in x that we see right along the x-axis there as we keep drawing in these little squares. So what are we going to try and do? We're going to build an integral that's going to add up a bunch of these little pieces here together as we move along from 0 all the way to 1 along this x-axis. Okay, we're going to add up a bunch of those together. So what will that integral look like? Because we're basing it on x, it's going to go from 0 to 1. And then the overall volume of this idea here is 4x squared being squared. So that's the, you could say the depth and the height, and then the overall width is going to be a dx. So I just need to figure out what this equals, and it's going to be adding up a bunch of these shapes to get the overall volume that would be created based on this flat base surface area with this 3D object projected up into it. complicated idea. Jot down questions if you have them as we go. So I'm just going to simplify this a second. We're still going from 0 to 1, but the overall function will simplify to 16x to the fourth. I need to integrate, so that means my power will go up by 1. I'll just write it like this. That means I also need to multiply by the reciprocal, so multiply by 1/5. I'm going to plug in a 1 and a 0. So if I plug a 1 into this, I get just 16 over 5. And if I plug a 0 in, I'm not going to get anything. So in the end, my answer is 16 over 5, which corresponds to answer D. Okay, this next question now, our base is going to be in the first quadrant now, so it's bounded by the x-axis, the y-axis, and then also the line x plus 2y equals 8, which is in standard form, and I've just shown you how I would simplify that and write it in slope-intercept form just so that our drawing is a little bit easier. From there, if we're looking at slope-intercept form, I know that my y-intercept would be the 4, and I could certainly figure out my x-intercept. I could plug a 0 in for y, kind of work backwards, and my x-intercept is 8. So that's going to appear in my drawing here in just a second, and I just want to make sure you understand where those numbers are coming from. The other difference is that now the area that the shape that is popping up is going to be a semicircle, a half circle, so the formula that we use might be just a little bit more challenging. So again, here's my poor excuse at a drawing. These semicircles are going to be perpendicular to the x-axis, so I'd be drawing a semicircle in there and in there and in there based on this distance from the x-axis to the line y equals 4 minus 1/2 x. And then from there, we're going to create a semicircle that's going to pop up. So those 3 red lines I just put in could correspond to maybe these 3 red lines, and then from each one we're going to have these semicircles popping up. Let's see if they draw this time. Come on now. Well, hopefully, there we go. Okay, we're going to have these semicircles that are kind of popping up. And so again, as we get closer to the x-intercept of 8, those semicircles are going to be smaller and the overall height will be shorter. So we just have to figure out how we represent that. So again, I want to figure out how do we come up with the volume of a slice of this. So right here, this will be kind of the thickness of this. Again, the drawing is not going to be very good, but we would have this width going out to there. Have a semicircle kind of coming up like that. We'd have another one that's kind of coming up like that. And so we're going to figure out how to find the volume of one of these and then add a bunch of these together. And as we do that, make the widths of these smaller. And so in that idea, we're kind of integrating. So the challenging part here is to realize that this length right here is the same thing as this. And to find the area, to find the volume of a semicircle, I'm going to have the width, which is related to this dx right here, and then the area of the front base here. But what I have for this red line here is related to this, and I need to know the radius of this semicircle. That's going to be half of this. So I need to know half of this, which would be half of this red line, which is half of whatever this y value is, right? Because whatever x value I pick here, I'm going to find the corresponding y value. That's going to be the entire base. I want half of this. So to kind of summarize this formula here, this is 2 of the radiuses. I need to divide this in 2. The radius would equal 2 minus 1/4 x for this entire picture. So as I try to build an integral that's going to help me out here, I just need to find the volume of one of these slices. That's how I kind of build the integral. Now, in the end, I'm going to be integrating from 0 to 8, but if I just think about the volume of one of these slices, I need to find the area of the semicircle, which is generally pi r squared, or in this case 1/2 pi r squared, because it's a semicircle, not a full circle. So 1/2 pi 2 minus 1/4 x being squared. That gets me kind of the surface area of whatever little shape I'm looking at, and then the width of this would create volume, so a dx creates volume. I just need to figure out how to do this. In this particular case, if we took enough time, we could certainly FOIL the 2 minus 1/4 x and then distribute the 1/2 pi and do some take some antiderivatives. I think it's possible to get started on this without a calculator. I'm just going to say use your calculator, plug this in, and you should get 16.755 as your answer. Oops, 755, which corresponds to answer C. Okay, and then our third example, now we're looking at the region in the first quadrant. It's going to be bounded by the parabola 2 minus x squared. And now it's going to be perpendicular to the y-axis. But again, we have a square, so that makes things a lot easier. So again, my attempt at drawing. What I want you to realize is that we'd have an upside down parabola. The y-intercept is going to occur at 2. And if we thought about it, the x-intercept would occur at square root of 2. Now these shapes are going to be drawn in this way. So as I go to this, they're going to be kind of like that. And these are squares again, so from each one, we're going to have some little, oh, that's bad, that is gross. Okay, we're going to have these squares that are popping out. Okay, and so now it's going to get taller as it kind of comes towards the x-axis, and I need to think about what the volume of each one of these things would be. So, really, if we're following the general idea, I need to figure out a way to represent one of these red lines here. This is now an x value. It's not a y value if I'm measuring from left to right. So I need to take this and actually solve for x. So I'm going to bring the 2 to the other side. Let's see, let me write this down here off to the side. So taking that equation, I would have negative x squared equals y minus 2, which means x squared could equal, I like keeping that first part positive, so 2 minus y, and so x would equal the square root of 2 minus y. So that's going to be how I would represent the length of that red line there. And now I'm going to build squares from that. So as I think about the integral that would create the volume of this shape, I'm going to be integrating, but because I'm working this way, I have to use y values. So I'm going to have my width for each of these things, whatever these squares that are popping up, is going to be a dy this time. So I need to use y values. So it's going to be from 0 to 2 for my limits. And it's a square, so each red line, the base of that would be the square root of 2 minus y, and then the height would be that same thing, so I'm just going to square that, and then the width would be dy, that's going to give it the volume, and as I integrate, the dy's become smaller and smaller, the error that I get gets smaller and smaller, eventually leading to that perfect overall volume. So in this case, pretty easy to algebraically simplify it. First of all, square root being squared just gets me 2 minus y with a dy. So from there, because of the way this question is written, there is asking for an integral interpretation, you would get answer B from that. But we certainly could go through and do some antiderivative business. This one actually isn't too bad. If I took the antiderivative, I would get 2x minus 1/2 y squared. We're going to integrate that from, oops, this would be a 2y there. Silly mistake. We're going to integrate that from 2 to 0. So notice if I put a 0 into this entire thing, it goes away. So I don't even need to worry about the second part of it. It's just going to be what happens when I plug a 2 in. So 2 times 2 is a 4 minus 1/2 times 2 being squared. So that would give me a 2 in the end. My answer is 2 for this. But for us, just answer B. So a very complicated idea here. Jot down some questions. I know my pictures aren't great, So maybe start with that. Anything you need visually would be good. But if the general concept is making sense, they generally phrase questions just like this, so you know exactly when you see the idea of cross sections in the question, you'll be in pretty good shape.